I'm trying to do here is move you first from where you have to manually tweak your parameters to using a built-in optimizer. And this is going to get to so this is much more sophisticated for two reasons. One, we don't have to keep track of our variables. We can just ask our model, hey, what are your parameters? And it will take care of all this updating according to the learning rate and stuff. And it can have multiple learning rates. It can do whatever it wants, okay? It also has an overall learning rate, which controls the overall progress, but each dimension has its own little mini learning rate. So you can see now that my loop has gotten much smaller even. So I'm going to use a model from PyTorch's neural net library. It's just a linear layer with one input and one output. That's just a simple linear model. And so I'm going to tell this optimizer that knows how to move down my loss function, get the parameters out of the model, and this will work generically, whatever that model is, and use whatever my learning rate is. Oh, I guess it should be above there. And I make a prediction, compute my loss, make sure that all of the previous slope values are gone, tell it to compute those values, and step. So this process here is going to be almost identical for any vanilla model you create, assuming you're doing regression and you can use MSE. Okay, so this is kind of your template. And so I've got some more blah blah here that explains what this looks like, but this linear layer here is just a one input, one output linear transformation. So W is a scalar, B is a scalar. When you ask for the model parameters, you can see that it's getting two parameters out, one for W and one for B. And then this training loop is just what you saw here. And so when I run this, this gives more or less the same answer. I don't remember what my learning rate is. Yeah, I have a much higher learning rate. I suppose it could, I don't know, I'd have to compare it to the previous, but okay. So that's standardized. Why am I doing two of these? Oh, yeah. So this is the M and B that we get out, and I'm drawing that line. And then this is actually showing the predictions for, these are the individual predictions for each particular data point in the training set. So this is the theoretical line that goes through there as computed by our training thing here, okay? And so let's see here. To be good programmers, let's factor that out into a function. So we're just going to put this into a function. And the reason I want to do that is because now I can convert all that code to make a model, train it with a certain number of epochs and learning rate. And then, oh, by the way, show the predictions. So what that lets me do is, let's say I want to prove that two linear layers without a nonlinearity between them gives me just a line. I can make one. Here's a model that's a pipe of two layers, or two linear layers. I train it, and I plot it. Sure enough, I get a line. So this is the template you can use to try different architectures. Let's add a ReLU in between. So I make another model, which is the exact same thing, except I got a ReLU in there. And I play around with this stuff. And you can see that I can start to get some different, and every time you run it, you'll get something slightly different depending on where we start. I got some exercises here and solutions. Here's a more complicated one. And here I'm showing you how to visualize it. So if you want to visualize something, you can just say with explain. You don't need this as E thing. And so if you say, this is my tensor sensor package, then it will draw the code and the dimensionality of whatever you're doing in here. So if you make this like 500, oh yeah, the dimensions are off. Then it shows you the dimensionality. Okay, so anyway, so here is, let's see, we did this one. Now we're stacking. And we got a different model. Anyway, so I've asked you with some exercises here to create different models and try them out. And you can see what happens when you use a sigmoid instead of a ReLU. You get this kind of very interesting fit. And what happens if you do 1,000, which is from the slides? You can play around with this as well. You can see you start to get this kinky thing. And you should try these learning rates. Like, let's see, if I try this as, okay, so here I'm training something with 1,000. What if I crank this up to a learning rate of, say, 1? What happens? Okay, that also works. It didn't explode, but woo, look at this, man. I got really low in my training, overfitting to the training data there. Let's try 10, see what happens. That didn't get very good. What if I do 1,000 or 100? Oh, wow. I'm surprised it actually did that. I was expecting it to explode. Yeah, so you can see this learning rate is just totally screwed, right? It's basically not getting anywhere. So the learning rate definitely affects this thing. And if I give it only a few epochs, that also affects it because it can't get too tight of a solution on the training set. So if I don't let it go too far, remember how I said that early training or stopping early is a way to regularize. Oh, look, I get a pretty decent curve if I don't go to 1,000. If I go to 1,000, yeah, it overfits again. So anyway, so this is the kind of thing you just want to get a feel for how these vanilla networks work and get an idea of how learning rates affect and how the number of epochs. And what if I only used 100? What happens? Okay, well, that's better, even though it's 1,000, right? So I gave it too much power when I had 1,000. That's one way to look at it. Okay, 3 minutes of questions. So that's fast and furious. But that's your 10,000 foot overview and some templates. Lucia.
Hi, I have a quick question about just like stacking these different things together, like in different shapes. I was wondering, is there a way just by looking at the shape of your data that you know whether or not you're supposed to put a ReLU or a sigmoid or any different combination inside?
Assume that you're going to use a ReLU.
Okay.
I use sigmoid only on the last layer and only if I'm doing a binary classification.
So because each of these processes is just going from one X to one Y bar. So it's not going to show up in the general shape exactly, like a line and then a curve.
Yeah, it's basically, we need some nonlinearity and it's the most efficient and seems to give a good answer. As for the network architecture, I don't think there's any general guidelines. I don't think you can just look at the data, but that if you've got, 1,000 features, you might need, more than a few of these. You might need quite a few, and you might need multiple layers. And people get experience and they go, oh, well, I'm going to start with really big, and then I'm going to shrink it down to something small to force it to get some features that are really representative, and then I can branch it out. And I think experience will start to tell you once you've looked at the dimensionality of the data, but maybe Yannet can comment.
What happens when you have tabular data? Pretty simple neural networks are going to define. So even like 2-layer neural networks are going to define. Then when you go to more complicated data, like text or images or things like that, then people have already experimented with a lot of architectures. So you are not going to come up with your architecture unless you have been learning this for a long time. So you're going to use somebody else's architecture. So that's kind of what happens in general.
Yeah, and that's the part that frustrates me the most. I was hoping that there was like a set of guidelines, like an algorithm. I'm used to analysis of algorithms.
There is a set of guidelines. It just changes all the time.
Yeah. Mm-hmm. Yeah, and for the longest time it was sigmoid, and then somebody said, no, this ReLU thing, and then all of a sudden it's ReLU.